Black holes are among the most fascinating and mysterious phenomena in the universe. These cosmic giants are massive in terms of power, yet they remain virtually invisible to us. A black hole weighing 2 to 4 million times the mass of the Sun is a prime example of their enormity. Over the last few decades, research into black holes has progressed from knowing almost nothing about them to gaining an increasingly detailed understanding. Recently, the world was stunned when Kaku announced that scientists had finally managed to get a glimpse of what lies inside a black hole. This breakthrough has provided new insights into details that the scientific community might have overlooked, offering a fresh perspective on the study of these enigmatic objects. Before delving into the recent findings by Kaku, it is essential to understand the basic concepts surrounding black holes. Although many people have a general idea of what black holes are, there are still gaps in widespread understanding. The history of black holes dates back to 1916 when Albert Einstein published his theory of general relativity. This groundbreaking theory predicted the existence of black holes. Although at the time the concept was purely theoretical, it took another 50 years for the scientific community to gather the first concrete evidence that black holes actually exist. In the 1960s, while studying the Cygnus constellation, astronomers observed an unusually bright blue star emitting X-rays. This star was not stationary but orbiting around a massive unseen object. Upon further investigation, it was discovered that the X-rays were being drawn into this mysterious object, which was eventually identified as a black hole. The discovery of this black hole, later named Cygnus X1, marked a significant milestone in astrophysics, providing the first proof that black holes were real and not just a theoretical construct of Einstein's imagination. Cygnus X1 is located approximately 6,000 light-years from Earth and is about 14 times more massive than the Sun. It is incredibly dense, possessing a gravitational pull so strong that even light cannot escape it, which is why it is called a black hole. The concept of a black hole is both fascinating and terrifying. A region of space where gravity is so intense that nothing, not even light, can escape its grasp. Anything that ventures too close to a black hole is inevitably pulled in, never to be seen again. This inherent danger only amplifies the need to understand these cosmic entities in greater depth. Following the discovery of Cygnus X1, scientists embarked on a quest to identify other black holes. Their findings revealed that there could be as many as 100 million black holes in the Milky Way galaxy alone. However, detecting them remains a formidable challenge due to their elusive nature. Despite this difficulty, estimates suggest that there are several million black holes scattered throughout our galaxy, underscoring the importance of studying these objects. One of the most significant concerns regarding black holes is their intense gravitational pull. The gravity of a black hole is so powerful that anything that enters it is compressed down to a point known as a singularity. In simple terms, black holes function like cosmic vacuum cleaners, drawing in everything within their reach. Research has revealed a chilling fact. If a person were to fall into a black hole, they would experience a process called spaghettification, where their body would be stretched and elongated to the point of becoming a single line of atoms. This process would be slow and agonizing, with death occurring long before the final form is reached. The sheer power and danger associated with black holes make it clear that they are not to be taken lightly. Despite the inherent risks, black holes continue to be a subject of intense study. The closest known black hole to Earth is estimated to be between 500 and 1,000 light-years away. While this distance might seem vast, it is close enough to raise concerns and questions about the potential dangers these objects pose. In 2021, a major breakthrough occurred when scientists released the first-ever clear photograph of a black hole, specifically the M87 black hole. This black hole, located in the center of the galaxy M87, was captured over several nights. Each photograph provided more data, which researchers meticulously pieced together to create a comprehensive image. The photograph of the M87 black hole revealed that it is not merely a single gaping void, as many had previously believed. Instead, it consists of 3 distinct layers. The first layer is known as the event horizon, which is the point of no return. Once an object passes the event horizon, it is inevitably drawn into the black hole. The second layer is the photon sphere, a region where light orbits the black hole. Any light that enters this area becomes trapped, unable to escape the black hole's immense gravitational pull. The third and final layer is the singularity, where all matter that enters the black hole is compressed to an infinitely small point. The singularity is a place where the known laws of physics break down and our current understanding of the universe ceases to apply. The revelation that black holes have multiple layers adds a new layer of complexity to their study. Moreover, no two black holes are identical. While they may share certain characteristics, such as the three-layer structure, the way they function can vary significantly. This uniqueness makes it even more challenging for scientists to study black holes directly. Traditional methods of scientific inquiry, such as sending probes or telescopes to observe an object up close, are not feasible when it comes to black holes. Any probe that gets too close to a black hole would be crushed into nothingness by the intense gravitational forces. Due to these limitations, scientists have had to rely on indirect methods to study black holes. They observe the radiation emitted by black holes as well as the gas and dust that surrounds them. By analyzing these emissions, researchers can gather valuable information about the black hole's properties and behavior. However, this approach is far from ideal, as it only provides a two-dimensional view of a three-dimensional phenomenon. Moreover, the fact that every black hole is unique, combined with the breakdown of the laws of physics at the singularity, makes the study of black holes an incredibly complex and challenging endeavor. Despite these challenges, researchers have made significant progress in understanding black holes. One of the most compelling theories about their formation is that black holes are created from collapsing stars. When a star exhausts its nuclear fuel, it can no longer generate the energy needed to counteract the force of gravity pulling inward. As a result, the star begins to collapse in on itself, becoming smaller and denser. If the star is massive enough, this process can continue until it becomes a singularity, a point of infinite density and zero volume where the laws of physics as we know them no longer apply. To gain a deeper understanding of black holes, NASA scientists turned their attention to the core of the galaxy M87. They observed a super-powerful whirlpool of hot hydrogen gas spinning at an astonishing rate of 1.2 million miles per hour. The sheer force of the spinning disk of gas should have caused it to fly apart, but it remained intact. This led scientists to conclude that a colossal mass, most likely a black hole, was holding the gas together. The study of black holes has also led to the development of new and intriguing theories. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations of gravity to describe a spinning black hole. Kerr's work showed that a spinning black hole would not collapse into a single point, as previously thought, but rather into a ring of fire or a thin disk. This spinning disk of matter, known as the ergosphere, surrounds the black hole and is the region where the laws of physics begin to break down. One of the most intriguing aspects of Kerr's solution was its prediction of the existence of an Einstein-Rosen bridge, more commonly known as a wormhole. A wormhole is a theoretical passage through space-time that could connect two separate regions of the universe or even two parallel universes. The idea is that if one were to fall into a black hole instead of being crushed to oblivion, they could be sucked down a tunnel through the ring of fire and emerge from a white hole in a parallel universe. The concept of wormholes has fascinated physicists for decades. In Einstein's theory of general relativity, space-time is described as the fabric of the universe, with objects of mass warping this fabric and creating a gravitational field that attracts other objects. A wormhole can be thought of as a shortcut through this fabric, connecting two distant points in space and time. However, wormholes remain purely theoretical, as no one has ever observed one directly. One reason for this is that wormholes are inherently unstable and would collapse almost immediately after forming. Even if wormholes could be stabilized, using them for travel through space and time would likely still be impossible. According to Einstein's theory of special relativity, the speed of light is the absolute limit for how fast anything can travel through space-time. Even if a stable wormhole could be created, it is unlikely that it would allow faster-than-light travel. Despite these limitations, the idea that black holes might serve as portals to other parts of the universe or even different times continues to capture the imagination of scientists and the public alike. The potential of black holes as pathways to other regions of spacetime is a subject of intense speculation and debate. One of the most intriguing concepts in this area of study is the Kerr wormhole. Named after mathematician Roy Kerr, who first described it using Einstein's equations of gravity. The Kerr wormhole is often visualized as a ring-shaped portal, similar to the looking glass in the story of Alice in Wonderland. Just as Alice's looking glass transported her to a strange world where logic didn't always apply, passing through a Kerr wormhole could potentially transport a traveler to another universe or time where the laws of physics are different from those we know. While the idea of using black holes as cosmic shortcuts is tantalizing, it is also fraught with challenges. For one, the intense gravitational forces near a black hole would likely make any attempt to enter a wormhole a one-way trip to destruction. Additionally, the very existence of wormholes is still a matter of debate among physicists. Some argue that wormholes, if they exist, would be incredibly unstable and prone to collapse under even the slightest disturbance. Others suggest that the extreme conditions inside a black hole, such as the intense radiation and subatomic forces, would make it impossible for anything to survive the journey through a wormhole. Despite these challenges, the study of black holes and wormholes has led to significant advances in our understanding of the universe. One of the most important developments in this field is the search for a theory of everything, a unified theory that could explain all the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. Currently, the most promising candidate for such a theory is superstring theory. Superstring theory proposes that all subatomic particles are not point-like objects, as previously thought, but rather tiny vibrating strings. These strings vibrate at different frequencies, and the way they vibrate determines the properties of the particles they form. According to superstring theory, the universe is a symphony of vibrating strings, with each note corresponding to a different particle or force. This theory not only unites gravity with the other fundamental forces, but also provides a framework for understanding the mysterious phenomena we observe in the universe, including black holes and wormholes. However, superstring theory requires the existence of additional dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. Specifically, the theory suggests that there are 10 or even 11 dimensions of spacetime. These extra dimensions are not something we can easily visualize, but they are crucial for the mathematical consistency of the theory. Physicists have developed various models to help us understand these extra dimensions, such as the idea of compactification, where the extra dimensions are curled up so tightly that they are effectively hidden from view. The study of black holes has also led to new insights into the nature of time. According to general relativity, time is not an absolute unchanging quantity. Instead, it is influenced by gravity and can be warped by massive objects like black holes. The closer one gets to a black hole, the slower time appears to pass relative to an observer farther away. This phenomenon, known as time dilation, has been confirmed by experiments and is a key prediction of Einstein's theory of general relativity. Time dilation becomes even more pronounced near the event horizon of a black hole. For an observer watching someone fall into a black hole, it would appear as though the person slows down as they approach the event horizon, eventually freezing in place. However, from the perspective of the person falling into the black hole, time would continue to pass normally. This discrepancy in the passage of time is a direct consequence of the warping of spacetime by the black hole's immense gravitational field. The study of black holes has not only deepened our understanding of the universe, but has also raised new questions about the nature of reality itself. For example, one of the most puzzling aspects of black holes is the so-called information paradox. According to the laws of quantum mechanics, information about the state of a system should never be lost. However, when an object falls into a black hole, it seems that all information about that object is lost forever once it passes the event horizon. This apparent violation of the principle of conservation of information has led to intense debate among physicists. One possible resolution to the information paradox is the idea of Hawking radiation, proposed by physicist Stephen Hawking in the 1970s. According to Hawking's theory, black holes are not entirely black, but instead emit a faint radiation due to quantum effects near the event horizon. This radiation would cause the black hole to slowly lose mass and eventually evaporate completely, releasing the information that was thought to be lost. However, the nature of this radiation and how it preserves information remains an open question. Another intriguing possibility is that the information paradox could be resolved by a deeper understanding of quantum gravity. the yet-to-be-discovered theory that would unify general relativity with quantum mechanics. Some physicists speculate that the singularity at the center of a black hole could be replaced by a quantum object, such as a Planck star, where the laws of quantum mechanics and general relativity are reconciled. This could potentially allow information to be preserved and even transmitted out of the black hole. The study of black holes has also led to new insights into the nature of space-time itself. For example, some physicists have proposed that the fabric of space-time could be made up of tiny discrete units rather than being a continuous smooth surface. This idea, known as quantum foam, suggests that at the smallest scales, space-time is a seething, chaotic landscape of tiny fluctuations. Black holes, with their intense gravitational fields, could provide a unique laboratory for testing these ideas and exploring the quantum nature of space-time. Black holes are among the most enigmatic and fascinating objects in the universe. They challenge our understanding of physics and force us to confront some of the most profound questions about the nature of reality, the structure of the universe, and the limits of human knowledge. Despite the many challenges and mysteries they present, the study of black holes has led to significant advances in our understanding of the universe and has opened up new avenues of inquiry in both physics and cosmology. As scientists continue to probe the mysteries of black holes, we can expect to gain even deeper insights into the fundamental nature of the cosmos and our place within it.